Hello everyone and welcome to this tutorial on Gaussian process regression in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last two tutorials we spent a lot of time discussing about decision tree frameworks, XGBoost, LightGBM, CatPost as well as the vanilla gradient boosting available in scikit-learn. We also learned how to train a support vector classifier, and we learned the importance of feature scaling as well as cross validation. We also looked at two different approaches to cross validation for hyperparameter optimization. It was grid search CV, which we did for the random forest model, and it was randomized search CV, which we did for the support vector machine model. By the end of it we have a good understanding of how to develop a classification model, wherein we worked with the MatBench isMetal data set to tune a classifier that can predict whether a material of various compositions is a metal or not, and that of course finds use in various core engineering disciplines. In today's class we will use a different data set which is more in the realm of civil engineering about concrete strength, and to do that we will use this Gaussian process regression framework which we have learnt in our lectures a little while ago. So what is Gaussian process regression and why are we talking about it? So GPR is a powerful and a flexible non-parametric Bayesian approach to regression. So there is a lot of words here. The first word is non-parametric, and we have already discussed what is a non-parametric model in our lectures. It is a model wherein the prediction depends on how similar the unseen features are to features of points in the training data set, and all types of kernelized models like kernel SVM, kernel ridge regression, and even decision trees are non-parametric models, but GPR is also a non-parametric model. Now the important thing is it is a Bayesian approach to regression. So not only does it predict a certain value, it will also tell you what is the error in the prediction that you are making. So how does it tell you the error? It tells you by being different from traditional models. So traditional models assume a fixed functional form like linear regression or a neural network. However, GPR defines a distribution over the possible functions that fit the data. So if you remember the previous lecture, we have a prior distribution which is a Gaussian process, that is a family of random variables that follow the Gaussian distribution, and then there was a posterior distribution. From the Gaussian process we refined the probability distribution that is followed by the functions, and from that we were able to make a prediction of every data point depending on how similar it is to points in the training data, and we are also able to give an error estimate. So the GPR predicts not only the output value but also provides uncertainty estimates, making it ideal for engineering applications and scientific modeling. So in engineering applications we are not just satisfied by predicting a value, we want to know what is the error bar in that value, and that is where GPR really shines. So the question is, why use Gaussian process regression? So the first thing is uncertainty quantification. Unlike many other regression models, GPR provides a confidence interval around each prediction, which is very useful. It is suitable for smaller data sets. GPR often performs very well when the training data is limited, which is a common case in various engineering domains, and it gives you flexible modeling just like other kernelized methods. You can choose a kernel RBF, polynomial, linear or Matern kernel, and GPR can model both linear as well as highly nonlinear functions very effectively. So you can think of various applications in core engineering disciplines. A mechanical engineer may be interested in modeling the stress strain behavior, fatigue life prediction, and surrogate modeling in finite element simulations. So if you want to develop a ML model for a finite element simulation, you can think of GPR. So you will also have an uncertainty estimate of the flow field or the temperature field or the pressure field at a certain point in space. In civil engineering, one may want to predict the degradation of a material used in construction, structural reliability analysis, and geotechnical modeling. An electrical engineer on the other hand may be interested in denoising of signals, identification of a system type, and performance prediction in analog circuits. whereas an aerospace engineer may want to predict the drag acting on an aerodynamic body, modeling of flight dynamics and uncertainty aware design of various types of experiments. And in chemical or biochemical engineering, you may want to estimate the yield of a reaction, the optimization of a process and catalyst design in the presence of uncertainty. So this uncertainty is where GPR really excels, right. Where experimental or simulation data is expensive or sparse, where you need uncertainty quantification for proper decision making, and where surrogate models are needed for optimization or control. These are all good use cases for Gaussian process regression models. So the takeaway is that when confidence in prediction is just as important as the prediction, you should use GPR. It is particularly useful for noisy or sparse data, and also when the relationship between the inputs and outputs is nonlinear or unknown. So GPR is not just about predicting a number, it is about predicting a distribution, which makes it particularly valuable in scientific fields where understanding uncertainty is critical. Okay. So the first step is now to train a GPR model. So in the following section we will prepare a data set for regression, right, and you could use a target like formation energy. Like I said, we will use a concrete strength data set here. Then you can train a GPR model using this sklearn.Gaussian process function, and you can visualize the predictions and uncertainty bounds, right. So for this particular problem we will take a data set from the University of California Irvine's machine learning repositories. So UCI, University of California Irvine, has a large collection of engineering repositories, and these can be very useful particularly for all of us who belong to the core engineering disciplines. So we will first install this repository. So you do pip install UCI-ML repo. You can see that if you put an exclamation mark, you can execute commands on the terminal inside the Jupyter notebook. So this exclamation mark, all it means is that we want to run a terminal command inside Jupyter. So that is why the exclamation mark is there. Now I have not shown the output of the installation here for brevity, but of course once you execute this you will get an output cell with the details of the installation procedure, which I am omitting here. Okay, so the data set we have picked from the UCI, University of California Irvine set of repositories is the concrete compressive strength. So this is the source, you can look it up. There is about 1000 samples here. We are focused on a regression problem wherein our goal is to predict the compressive strength of concrete based on the composition of the mixture. So what are the features that we are working with? These are the features which are there in the data set. The density of the cement in the mixture, which is the quality, the amount of slag used in the blast furnace, the content of fly ash in it, how much water is there in the mixture, what is the superplasticizer, what is the number of core aggregates, fine aggregates, and what is the age in days of the concrete sample. And the target variable is the concrete compressive strength in megapascals, which essentially is the strength of the concrete after a given curing time. So the data source for this is the concrete compressive strength from this UCI dataset. So this is the link to the UCI database. We are picking the 165th data set from this repository. There are, like I said, there are various repositories from different branches of science and engineering. So you can definitely take a look at the various data sets there, because for computer scientists there are other data sets, but for engineers we do need more interesting data sets to work with. So from the UCI ML repo library I am importing fetch UCI repo, and then I am using the fetch UCI repo command with this 165th ID, like you saw in this link, that is the 165th data set that we are looking at. Okay, so once you have fetched the data set, you can get the features here as the X data matrix, and then you can get the targets in the Y vector, and you can then print whatever is there in the metadata, and then you can also print the variable information through these commands. So what happens when you do that? So this is the metadata, this is the ID of the data set, UCI ID. the name of the data set is concrete compressive strength. Then the repository URL is also given here in case you want to open this URL at your own end. The data URL is given, so the data is available in a CSV file, data.csv, and this is the abstract of the data set. So concrete is the most important material in civil engineering. The concrete compressive strength is a highly nonlinear function of age and non ingredients, and the area of this data set is physics and chemistry. It involves a regression problem, a multivariate problem, and then the number of data points is 1030, number of features is 8, right. So these are the features which are being used, which I had discussed earlier. Alright. The source of the paper is also given here. So if you are interested in the original source of the data, you can look up this paper here as well. Okay. So you can go through this metadata in more detail, and then you will understand what exactly is being said here, but it is a valuable piece of information which is being provided in this metadata, right. And then like I said, that these are the kinds of features that we have used here, right. And finally we want to predict a continuous target variable, that is why we are using Gaussian process regression. As I had mentioned in the class, it is also possible to do Gaussian process classification, but we will not be discussing it in this course due to the lack of time. Alright, and it also gives you the units of each of these features as well as the target variables. So all of these are given in kilograms per meter cube. So whether you are looking at the slag, fly ash content, water content, the superplasticizer content, the large aggregate, sand and smaller particles, all of this is given in kg per meter cube. The age is the only factor which is given in days, right. So this tells you an idea of the units of each of the features, and you can see that none of the data points in this data set have any missing feature. So that is good to go, right. If you had any missing data, then you would have to clean the data set. So that is where the pre-processing of the data, wherein you do data cleaning, can be important in certain instances. In this particular case, we are fortunate that all the data points have all the feature values, so there is no missing values. Okay. So let us go ahead and get started. So we will first use GPR with a radial basis function kernel, which assumes a smooth continuous relationship between the features and the target. So if you remember this RBF kernel, it assumes a functional form like this, right. So you are looking at the distance between the feature vectors, right, of various data points as you are making the prediction, and this is the gamma factor that we already discussed. So this is a RBF kernel, and that is used to model the covariance of the predicted values, right. If you remember, we have to assume a certain form of a covariance in the Gaussian process regression framework. If you look up the lectures, you will remember. Okay. So these are some of the standard things that we do when we set up an ML model. By now you will be familiar with all of this. You have to do a train test splitting. For models like GPR, SVM, you have to do standard scaling. It is particularly useful to do that. Then you can import the Gaussian process regressor function. You have to import the model that you want to use, and in this case it is available in sklearn's Gaussian process library, and we are also importing these kernels. We are importing the RBF kernel, the constant kernel. Later on we will also use the white noise kernel. You will see that only when you include the white noise kernel to model realistic noise, then the model actually is doing well. Okay. And since this is a regression problem, we are not going to look at things like accuracy, ROC, AUC, F1 score, precision recall. Instead we are going to work with our more conventional loss function like the mean squared error. We are also going to look at the R squared, the goodness of fit, right, or the coefficient of determination, which tells you how well the model is able to explain the variance in the data set. Okay. So now here we are splitting the data set into train and test values, and here we are using a test size of 20%, and 80% of the data will go into the train set. Then we are doing a standardized scaler. We are using the standard scaler to scale the features. Like I said, you train the scaler on the training data and then apply it to the testing data through the scalar or transform function. Alright. So now we are defining the kernel here, which is the RBF kernel. We have to define the length scale as well as the length scale bounds here, and then we can train the Gaussian process regression model. Okay. So you have to specify the kernel, the random state, and the number of restarts that the optimizer will do, and finally you are able to train the GPR model. And with this fitted model you can make predictions on the scaled training data and then on the scaled testing data as well. Once you have the predictions, you can look at the mean squared error between the training and the prediction data, and similarly for the train R square you can look at the R squared score function on the train actual wise and the predicted wise. A similar exercise should be done on the test set to get the test MAE and the test R square. And at the end of it you want to print all these results, right. So you have the train MSE, train R square, and the test MSE and the test R square as well. So these are the kinds of results that we obtained. Look at the train model performance, it is quite good, MSE of 0.87, the R squared score of 0.99, but look at what happened in the testing. The MSE is so high and the R squared value is negative, right. So that means that our plain vanilla RBF kernel is not working as well, right. And what could be the reason behind this? The reason behind this could be is that when we are doing the RBF kernel is just the exponential part of this, right. So we are not setting a scale for the problem here. So what if we multiply this RBF kernel by a constant kernel, right. So this constant kernel will set a scale for the covariance. So that is one way we can think of to improve the flexibility of the kernel as well as the flexibility of the GPR model. So that is what we are going to do next. We are going to scale the RBF kernel by a constant value. So let us go ahead and do that. So to improve the flexibility of the GPR model, we can combine the RBF kernel with a constant kernel, and the constant kernel helps model the overall signal magnitude while the RBF kernel captures the smooth variations in the data, right. So we have to set a scale for the problem. So now we are also importing the constant kernel as C, and what we are doing is we are taking a constant kernel in this range and then multiplying it by the RBF kernel which was already defined earlier, right. So this is the constant kernel in this range, and then this is the RBF kernel. Of course the optimal value will be decided after the GPR training happens. Okay. So this code will train the GPR model, and then like we did above we can predict the values for the train and test sets, right, and finally evaluate the mean squared error as well as the R squared score on both the training as well as the testing data sets, and we can print the results here. So this is quite similar to what we had already done earlier. So now what you see is in this case the test mean squared is still really bad, it is in fact become worse. The train mean squared error 0.87 and 0.9969 is very similar, but actually the test mean squared error has gone bad. So what do we do to fix this? So to fix this we extend the Gaussian process kernel by adding a white kernel to model any observational noise explicitly, right. So there can be noise in the data, and this is especially true in engineering settings. So to account for that noise in the data itself, we combine the constant and the RBF kernels and add the white kernel to account for random noise or measurement errors in the data, right. And this composite kernel often leads to more robust predictions, especially when the data set contains noisy observation. So from the sklearn Gaussian process kernels we are also importing the white kernel and the dot product operation. So we are splitting the data set, standardizing the features through a scalar, and this is the important part wherein we have a constant kernel multiplied by an RBF kernel, and we are adding this white noise kernel to it. Alright, so now we again train the GPR and then fit the GPR, and then this will allow us to make predictions as well as evaluate the mean squared error and the R squared score on both the training and the testing sets. And now the results are much more nicer. The train of course error came down because we are also including noise in the framework, so that can sort of skew some of the predictions on the training data, but the nice thing is that the test mean squared error has fallen down drastically and the test R squared score has also gone up. So that is a really nice thing that we have achieved. So finally what we have done here is we have assessed the importance of the kernel on the model performance. Because GPR uses kernel functions to define the similarity between data points, the choice of the kernel directly affects how well the model fits and generalizes, and these are the metrics that we obtained. The test MSE and R square was the best when we used the constant times RBF kernel plus a white noise kernel to model the noise in the system, right. So RBF plus white kernel gave the best results, likely due to the flexibility and the ability to handle noise, and RBF alone with or without a constant kernel was not able to perform as well. And the key takeaways are that different kernels impact the GPR performance, and adding a white kernel helps model noise and improve generalization, and it is definitely important to experiment with various kernels and to evaluate on a test set using appropriate metrics like the MSE and the R squared score. Now in regression, right, what is a good analysis without a parity plot? So if you remember, a parity plot is a diagnostic tool used in regression to visualize how the model's predictions match the target variables. So on the x axis we have the ground truth, the actual values, and on the y axis we have the predicted values from the ML model, and a perfect model would have all the points lying on the y equal to x line indicating the perfect predictions. So it is useful because a closeness to the diagonal indicates high prediction quality, and systematic deviations on the line may allow you to diagnose things like bias, so under prediction or over prediction, systematic, or non-linearity or model limitations. Let us say your parity plot makes it seem like so this is the predicted values and these are the true values, and let us say that this is y equal to x and your parity plot is something like this. So you mean systematically you are under predicting in this region, right, and then you are over predicting in this region. So those kind of things you will be able to find out. So like I said, points above the line are over predictions and points above the line below the line are under predictions, and the spread around the line reflects the model variance or the noise in the data. Okay, so let us plot these parity plots now. So we can include both the training as well as the testing points. The train is in green, test is in blue, and then we also have the y equal to x line which we can plot here, right. Basically we just plot the same thing on the x and the y axis. And on the x axis is the actual compressive strength, the ground truth, y axis is the predicted compressive strength. So this is the parity plot for when we are using the constant times the RBF kernel plus the white noise kernel, and you can see that this is quite a nice parity plot. There are some points which are not as well predicted, but most of the points lie along the ideal y equal to x line. So that is a really nice thing that we have been able to do using this GPR model. What I encourage you to do is to use some of the other regression models like XGBoost, LightGBM, CatBoost, then you also have support vector machines, right. You later we will read about neural networks. If you go back, you have linear regression, lasso, ridge regression. In this course you have learned such a wide gamut of machine learning models that I would really encourage you to repeat these tutorial exercises with the more complex machine learning models and see whether they can outperform Gaussian process regression, which is what we have done here today. Right. You can also make a residual plot which is used to evaluate the quality of a regression model by analyzing the errors between the predicted and the actual values. So that is just the true and the predicted values, the difference between them, and you can plot it on a figure, right. So this is the residual distribution. You can see that it is roughly following a Gaussian distribution. Now this also links to the kind of assumptions we have been making. Typically we are assuming that the errors are following a normal distribution with mean 0 and variance sigma square, where sigma is an estimate of the irreducible error. So, this is actually proof that the errors that we are making, they are following a Gaussian distribution, right. So, that is a nice thing to see, and you can see that how far the errors can go, right, in terms of the numbers. And finally, because GPR is a probabilistic technique, you can also use it to plot an uncertainty band, which is a visual representation of the model's confidence in its predictions, and is especially useful in GPR, which naturally provides both mean predictions and standard deviations. So, what this shows is the predicted values, right, they are shown as a line, and the shaded area around the prediction represents the confidence intervals, usually set at 95%, and if you look at a normal distribution and you set the confidence interval at 95%, how you can get the interval is prediction plus or minus 1.96 times standard deviation. So, this 1.96 number comes from 95%. If you look at the distribution plot, the cumulative distribution function, you will see that. Okay. So, now why it is useful? Because it quantifies the model uncertainty across different predictions, and wider bands indicate higher uncertainty, whereas narrower bands imply more confident predictions, and this helps assess model reliability and data sufficiency in different engineering regions, which could be particularly useful in core engineering disciplines. And our interpretation is, if the actual values fall within the band, the model is performing reliably, whereas consistently wide bands may signal data sparsity in that particular region of the feature space, or noise in the model in that particular region of the feature space. And sudden spikes in uncertainty may suggest regions exactly where the model lacks training example. So, then you can go back and get more data in those regions of the feature space, and then you can retrain the model and you will be good to go. Alright, so for this we will need NumPy, we also need PyPlot from Matplotlib as always. So, these are the test values, right, and then we are sorting them, right, based on the predicted values, and then you are actually providing this confidence interval, right. The predicted value minus 1.96 times the standard deviation, and plus 1.96 times the standard deviation. Okay. So, like I said, the black is the actual data, the predicted is more smooth, of course it cannot capture all the variations, and then you can see the confidence interval. So, regions where the confidence interval is spiking, you can add more training data to reduce the uncertainty band from GPR. So, finally, like I said, we will also discuss a different feature importance analysis than SHAP, which we discussed with the decision trees. This is permutation importance, and how this method works is it measures how much each feature contributes the prediction by randomly shuffling feature values and observing the impact on performance. So, if you have the values of a feature, you will randomly shuffle them and see how worse the model performance, and if a model performs really worse, that means that particular feature is really important, because incorrectly specifying that feature led to wrong predictions, right. So, from sklearn.inspection we are importing the permutation importance model, and then here we are fitting this from model selection the learning curve function. So, this is how you can compute the permutation importance, right, on the GPR model that we just trained, and you can plot this here. So, you can see that the age of the concrete is the most important feature. If you swap the values randomly of this particular feature, you will make really terrible predictions. The cement density, blast furnace slag, water content, superplasticizer content, fly ash content, these are all in reducing importance. The number of aggregates is the least important feature. Alright, so this brings me to the end of this particular tutorial on Gaussian process regression. So, I hope you learnt how to train machine learning models with Gaussian process regression, where the kernel that you choose is really important. So, today we saw how we can use an RBF radial basis function kernel, a constant kernel multiplied by RBF, and we can also use a white noise kernel which allows you to model the noise in the data inherently. The good thing about GPR is you can get an uncertainty band, you can know which regions of the face of the function feature space are underrepresented, you can add more data points there. You can also get uncertainty estimates which are very useful in engineering applications, wherein you have to make decisions based on the model predictions. And of course the UC Irvine machine learning repositories has a nice collection of various science and engineering data sets that you can try on your own, and I strongly encourage you to try other machine learning models. We have done GPR here, but on the same data set you can try a host of other models, and similarly when we did decision trees you can try other machine learning models there as well. So with this our journey into machine learning continues. In the next lecture we will start delving into neural networks, which will be the last frontier that we will cover in this NPTEL course. Thank you very much for joining today, and I look forward to seeing you in the next lecture. Goodbye.